Hello. Thank you guys all for coming out today to the 2022-2023 Bridge Team Symposium presentation. I'm Noah, this is Jared, and this is Logan. And we're going to start out with an introductory video, and then we'll get into the presentation. Welcome to the 2022-2023 Collaboratory Bridge Project. This year, the Bridge Team has partnered with Forward Edge International to design a maintenance access and pedestrian bridge which will grant them access to a new school building that they have been constructing over the past year. Forward Edge is a Christ-centered relief and development organization who partners with God to transform lives through children's programs, missions teams, and practical training. The ministry provides healthy meals, safe drinking water, medical checkups, tutoring, and income-providing initiatives to over 100 children and their families. Forward Edge has recently purchased a property just south of their existing ministry center where they have begun construction of a new school building over the past couple of months. Currently, there is access by a much longer route, but a shorter and more accessible route is desired by Forward Edge. Through hard work and the guidance of industry professionals, the Bridge Team has designed a concrete box culvert to meet the needs of Forward Edge and their Trigo Miel Ministry Center.
The team selected a concrete box culvert as the structure type based on the loading, durability, available labor, required span, and geotechnical considerations. The team has designed the structure to withstand pedestrian and vehicular loads, including passenger vans and a water truck. The team has used AASHTO's 20-ton H20 truck and 25-ton design tandem truck. Steel and concrete structures tend to be most effective for these larger vehicular loads. Additionally, considering issues like corrosion in steel and termites in timber, concrete's durability is attractive. Finally, concrete is familiar to the labor force in the region and could be mixed on site, which would make good use of the relatively inexpensive labor available there, making it a cost-effective material. A culvert was selected based on the short span length and the culvert's ability to distribute loads well over the clay soil on the site. The team used software to model the culvert and observe the demand on critical cross sections and designed slab thicknesses and steel reinforcement to provide enough capacity to exceed those demands.
The team will be traveling down to Oaxaca, Mexico for construction of the concrete box culvert upon the conclusion of the school year. To ensure a successful bridge build, the team has designed formwork for each portion of the bridge, a detailed construction sequence, and constructed a practice wall with the intent to familiarize the build team with construction processes that will be used during the build. With the help of local labor, the team plans to have the bridge complete and up and running with bridge construction within 2 weeks of the beginning of the trip.
Yeah, so the project started at the beginning of the school year in September, and obviously we are now in April 2023. And at this point in time, we have completed to 100% the structural design calculations, the construction sequence, and the final drawing set that will be used for construction. The next and final step in the project is to send a team down from Messiah to Mexico to go and construct the bridge. With that, I'll pass it over to Logan.
Thanks, Noah. Yeah, so as mentioned in the video, we selected a concrete box culvert as our structure type. The image on your screen is a cross-section view of that structure, as well as it has the existing topography shown with a dashed line. I want to highlight some of the key geometric features of the structure, and as well as some of the challenges that brought us to those features. So one of those is the fact that there are two cells separated by a pier. So whenever you're bridging across a moving body of water, it's really important to provide a large enough hydraulic opening to convey the channel effectively. At the same time, though, we need to make sure that we're providing a structure that's strong enough to provide to be able to support the loads that we're asking it to support. So we opted to provide a pier for that reason, to make the structure stronger. But we decided not to put it in the middle of the span, rather to have two cells of different sizes. So the one cell on the right, the larger one, will be for carrying the stream during normal flow. And then the second cell, the idea with that one is that will be used, that one will come into play during higher flow events. So then both cells will be used. That way our pier isn't in the stream during normal flow. So it's not in the stream all the time, being subject to scour. which is basically wearing away at the pier due to the water and the sediment in the water constantly bashing up against it. And then that's not always in there. The pier's not always there impeding the stream flow as well. Another thing I want to highlight is the fact that that top slab is not flat. There's a crest in that. The reason for that is that we want to minimize the approach ramp lengths coming up to the bridge. The reasons for that are, one, we don't want to take up any more space than necessary on Trigo and Miel's properties. And additionally, we want water to be able to flow around the bridge in a high flow event. So having shorter approach ramps allows water to go around and minimizes any flooding upstream. As you can see in this image, we have, for any given slope coming up to the bridge, we can actually get a larger clearance under a vehicle with the crest versus without it. So again, that crest allows us to maximize the slope of the approach ramps and therefore minimize the length of them. And then one last feature I want to point out is this existing wall that's on the right end of the culvert in this image. This was one of the biggest challenges that we dealt with in the project because this wall was actually built while the project was had already started. So design had already begun. It was built in the fall 2022, which there's an image there on the right. That's a photo of construction. And then on the left, there's an image there of a plan view of showing you the approximate location of that wall. It's actually right about where the team had been planning on locating the southern wall of the culvert. So we had to deal with that apparent conflict. We had a couple different design iterations. The top image there is our first, the bottom is our second, and then the image you saw earlier was what we finally came up with as our final design. Some constraints to keep in mind here. One, we can't expect this existing wall to carry any loads that we're expecting the culvert to deal with, since it wasn't designed for that. Additionally, we want to keep that hydraulic opening as large as possible for the stream. And third, it has to, of course, be constructible. So the issue with this first design on the top is that since we're stopping the culvert at the existing wall footing, that reduces our hydraulic opening. So that's not ideal. In the second iteration on the bottom, issue there is that we're concerned about putting load on that existing wall footing. As you can see, it's with the foundation having that sort of dog-leg shape around the existing wall. Both of them also have some constructability issues, and not the easiest to construct, since it's with that first iteration, it'll be difficult to backfill and compact the backfill between the existing wall and the culvert wall. And in the second iteration, that sort of dog-leg shape around the existing wall footing is a little bit more complicated to form. Ultimately, we came up with this final design here, where we actually cut away at the existing wall footing and just bring our culvert foundation right up against the wall. And then we additionally cut off the top portion of the existing wall so that we can have the top slab cantilever over. That way, we're not having vehicles driving over the top of that existing wall, putting load on there that it's not intended to handle. One other challenge with this I want to point out is that we actually don't know our structure height, and that's because we don't have a highly precise footing depth measurement for the existing wall footing. So as a result, we ended up putting a variable X in our drawings, as you can see on the right, and that's the original wall height plus the existing footing height. And we made some expressions throughout our drawing set for height dimensions and also part quantities based on that dimension. So one of the first steps when we go out to construct the wall, or the culvert rather, is to actually determine that X dimensions length. And with that, I'll pass it back to Noah. He's going to talk about construction.
Thanks, Logan. So a large part of what the team worked on this year is a construction schedule and construction sequence. And its main function is to keep the team on pace to finish construction in the 2-week period that we've planned. So 3 construction tasks that I'd like to highlight are the initial excavation, the existing wall demolition, and the 3 concrete pours. So upon arriving to the site, the team plans to excavate the proposed bridge location. We're going to have side slopes at a grade of 2:1, and then we're also going to over excavate to replace some of that clay soil with a more reliable coarse aggregate subbase. Whose primary function is really just to combat differential settlement of that clay soil and also just give a stronger surface for the bridge to bear on. The next step is going to be partial demolition of the existing wall. So as Logan mentioned before, the structure geometry that we've selected requires that the top 1 foot and 3 inches of that wall be removed so that we can cantilever the top slab. And also the footing on the north side of that existing wall will be removed so that the bridge can be cast up against it and the bottom slab can be flush with that existing foundation. So the team decided to break up the construction into 3 larger concrete pours, which include the bottom slab pour, the wall and pier pours, and the top slab pour. The main motivation behind this decision was just to make it easier to recruit and schedule local labor, as well as give us time between each pour to get things set up, as these are more labor intensive work days. However, the downside to this, as opposed to having more smaller concrete pours, is that we won't be able to reuse formwork as much. So more unique sets of formwork will be needed. So when talking about cast in place concrete construction, formwork is a critical part of that design, as it holds uncured concrete in place until it has reached its full strength capacity. And when designing formwork, it's also important to remember that you need to set up the formwork and then strip it once that concrete has cured. So here you can see our foundation formwork design. The main function of this formwork is just to hold the bottom slab in its design geometry. To do that, we are planning on using rebar stakes on timber boards to hold that concrete until it's reached its full capacity. Here you can see our wall and pier formwork. The team's going to build some timber panels that will be set vertically and supported by timber braces with embedded anchors that will be stuck into the bottom slab. Then finally, our top slab formwork and shoring, which is probably the most involved with design, as a structural analysis needed to be done because this formwork and shoring is going to be supporting the full vertical load of that uncured concrete until it's reached its full capacity. So Forward Edge requested a cost estimate and a bill of materials about halfway through the school year, so in December. And at that point, there was a lot of uncertainty in the cost of tools, materials, and the labor that would be needed. So we gave them an initial estimate and used a pretty conservative cost multiplier just so that we weren't grossly underestimating our cost. But as the year has progressed and we've been able to refine our budget, we came up with a number of $16,600 approximately for the whole project. So with that, I'd like to hand it over to Jared.
Thank you, Noah. So I'm going to be talking about the practice wall construction. As most of you know, we're going down to build the bridge, and we wanted to go through some of the steps that it would take to get through that construction cycle and that construction sequence and make sure that we have everything polished out before we head down to our 2-week time frame in Oaxaca, Mexico. So we worked with Andy and a bunch of the grounds people, and we determined that we were going to build our wall here. And so some of the steps that we wanted to practice before we head down were excavation, the building of the formwork, placing the rebar, pouring the concrete, and then stripping the formwork. And as we were doing this, we found out that there are some different difficulties with certain parts of these steps. And we wanted to make sure we had that ironed out before we head down. So in these 3 pictures here, the team is on the left, the team is building and placing the rebar for the formwork of the foundation. In the middle, the formwork is completed for the wall and the wing wall itself. And then on the right, there's our completed wing wall and foundation right there. So some challenges and takeaways that we took from this were that we had problems with just some simple problems with our formwork. So we decided that we're going to use a jig while we're down in Oaxaca, Mexico. And then obviously, since we are unable to bring a rebar bending tool through customs, as we found out through previous projects,
we decided that we would make our own. So we came up with that nifty little thing up there on the left. And so I'm going to pass it back to Noah to finish up the presentation. Yeah, so we just like to thank all these people for allowing us to have a successful project this year. They were all critical to what we've been able to do. And we'd like to thank all of you guys for coming out to see our presentation. And now we'd like to open it up to any questions you may have. So the question was why the 2-inch gap between the cantilever and the existing wall?
Yeah, I can take that. So main thing there is that we don't want any question of whether we're going to be actually putting load on that existing wall. So we left a gap in there so that over time, as the culvert settles a little bit into the ground, we have a little bit of extra wiggle room there to make sure that we're not actually coming in contact with that existing wall.
Yeah, so the question is what kind of safety features are going to be put on the bridge? So right now, we are planning on building timber railing along the side of the bridge for pedestrians that may be crossing. And that's something that's going to be, done whenever we're down there. Probably embed brackets into the side of the structure and then build the timber railing down there. The question is, how confident are we that we can finish the construction in 2 weeks? A lot of that will probably depend on the weather down there. And right now it's pretty dry down there, so we're confident we can get it done in 2 weeks, but things happen and you got to be ready for those. So we're pretty confident, but we're also prepared for things to go a little crazy.
If I could mention one last thing, I forgot to mention about that 2-inch gap. Another reason for that is so that it's a little more constructible, so that we can get our formwork in and out of there as well.
So I think that's all the time we have.